Okay, we're going to continue on here, chapter 10. We've been talking about energy, and we talked a lot about two main sort of processes of energy, which is obviously exothermic and endothermic. And again, as we've talked about, that is where we release energy, and endothermic is where we absorb energy. And we also talked about energy diagrams that sort of correlate to each of these in a exothermic sort of energy diagram. We look something like this, where the energy of our reactants are higher than the energy of our products. So in order for our reactants to get down to our products, overall energy has to be sort of released from the system there. And that would be our exothermic sort of diagram. Our endothermic looks a little bit different. Looks something like this, where we have our reactants, which is our starting material in a chemical reaction, lower in energy than our products. So in order to get up to the energy of our products, energy has to be absorbed in that case, which would be an endothermic type of situation. Remember that in order for a reaction to sort of occur, there is sort of a hill of energy or minimum amount of energy that's required for a reaction to take place. And that is the difference between our reactants and really the peak of that energy hill there to the top. And that is sometimes abbreviated as E of A, which is the activation energy. So as we talked about, that's sort of the minimum amount of energy that's needed for that reaction to take place. Not all collisions will result in products being made. So just because a couple of reactants sort of collide with one another, they do have to hit each other in the right spot. They do also have to hit each other with the right amount of energy to get up and over the hill there to the other side. So it is possible, you can have collisions in the wrong location with the wrong amount of energy that will not allow products to be formed. Now, another area that we talked about as well is really when we think about energy, one of the most common sort of ways that energy is displayed in chemistry is as a difference between the energy of our reactants and the energy of our products. And that is what is known as the delta H. And the delta H is the change in enthalpy. And that basically is the heat of a particular reaction, how much energy is being absorbed or how much is being released as the reaction is taking place. And typically speaking, our delta H values are negative for something that's exothermic. Delta H values is positive for anything that is endothermic. One of the ways that we could calculate sort of the change in enthalpy is to take the enthalpy of the products minus the reactants. And that goes back to what we were talking about with state functions, with the idea that really the two most important spots along the way is where you start and where you end. It doesn't really matter how you get there. It could be lots of individual reactions to get there, but where you start and where you end is really the most important thing. And in a reaction, where we end is our products, where we start is our reactants. So if we were to do the delta H of the reaction, we would take all the delta H values of our products minus all the delta H values of our reactants. And remember, if you're just given the equation, you basically could go to a table and sort of look up these values. And these values are found based on what the substance is. And it's also really important to look up the value based on the state that the substance is in. So you will find different values if it is liquid, gas, or aqueous when you go to that table. Also on that table, as we saw towards the end last time, things that are really in their sort of natural state, uncombined or anything like that, means that they will usually have a delta H value of 0. So I think we had like H2 or something like that in the previous example, and it would be 0. The other important thing when we do this type of calculation is we do have to take into account the sort of stoichiometry of the equation. And that is the numbers that come in front in a balanced equation, the coefficients. These are what are referred to as the moles of each of those things. So if we were to do the calculation for this, we would take the delta H, would equal our products. And on the product side, we have 2C. So we would take 2 times the delta H value for C that we would find in the table. That is all the products. We would then subtract it from 2 for the coefficient for A times the delta H value for A that we'd find in the table, plus our second reactant, which would be 3 times the delta H value that we find in our table for B. Again, we would add all that up, and depending on whether it's negative or positive as to whether or not this reaction is exothermic or endothermic. The values that we typically find in this table are in kilojoules per mole. Thank you. And when we multiply by these coefficients, these are technically moles, so the moles and the moles sort of cancel, and you're left with like kilojoules as the units at the end of that. Any questions on any of that stuff? Yeah. You would use this equation where they would ask you, you know, what is the change in enthalpy or the delta H for a reaction? And typically what would happen in that situation is you oftentimes will be given just a balance equation, and you would have to go to a table, and usually you can find these tables in like the back of the book or something like that, and you would look up the values for these. So, and that will give you overall basically, is this reaction sort of releasing energy? Is it absorbing energy? And that's really the difference between our reactants and products location, which goes back to these graphs. When we look at our exothermic, our product number is lower than our reactant. So basically, when we take a smaller number for our products minus a larger number for our reactants, we're going to end up with a negative number. And that's why our delta H is negative in that situation. And that's opposite in an endothermic. In an endothermic reaction, our final state, which is our products, is actually a larger number than our initial state in terms of energy. So when we subtract those two, we end up with a positive number. And that's why delta H is positive for a endothermic reaction overall. Any questions on that stuff there? All right, so I think we did one at the end there. So why don't we do this one and see what we end up with. Let's calculate the enthalpy value or the change in enthalpy, which is the delta H. That is what the change in enthalpy is. Based on these guys here, and again, these are values that you would find in a table to see what you come. Okay, let's take a look. So once again, if it's not given to you, these are again table values that you can look up. Once again, you want to make sure that you also look up the correct states of everything. So here we would take our delta H of our reaction. It's equal to our delta H of our products minus the delta H of our reactants. So starting on the product side, we have 16 of the COs. So we will take 16 because of the coefficient, which is really the moles, and times it by the value of CO that we got going on there. And that's really kilojoules per mole. We will then add it to 18 times the value there of our H2O, which is minus 286. And then we will take care of all of our products there. We will then subtract it from our reactants, which is 2 times our C, whatever it is there, minus 208. And 25 times our oxygen, which is actually 0 kilojoules per mole, as it is in a standard state. So if we do all that there, we will end up with something like minus 6492 kilojoules in this case. In terms of significant figure wise, since we are adding here, that looks like a whole number, that looks like a whole number. So we'll take it to a whole number in this case, since we're basically adding and subtracting in this particular case. Endothermic, exothermic, this one is exothermic, and I know that regardless of the number, I see a negative sign, so that tells me it is exothermic. Any questions on that one? I feel like that's the one we did last time at the end. I could be wrong, but that is the one we did last time at the end. So let's take a look at another, yeah. It doesn't technically, because these are kilojoules per mole, and all these coefficients are actually moles. So when we multiply them, that's kind of where the moles cancel out by the coefficients. They're technically the moles of each of those. Some people will leave it in kilojoules per mole, even though technically it cancels out. But that's technically where the moles part would cancel out from. Yeah. You'd be fine on that one. Yeah. So let's take a look at another one here, and I think we might have done that one. So let's just take a look at it together on this one. Once again, here we would take our products minus our reactants. So we'll do our delta H, which would be, again, our delta H of our products minus our delta H of our reactants. And again, our coefficients here, which are really the moles of each of these, we're going to multiply by. So we'll start with the 12 times the CO2's value, which is minus 393.5 kilojoules per mole. And we will then add it to 6 times our water value here, which is minus 286 kilojoules per mole. And again, that takes care of pretty much of everything that we got going on in terms of energy on our product side, basically where we ended and finished. And we're going to basically take that from where we started, which is our reactant side over here. And we have 2, which again is technically 2 moles times our value of 4904 kilojoules per mole. And we're going to add that to 15 times our 0 kilojoules per mole. So oxygen is in a standard state, and delta H is for anything in a standard state, uncombined, just really like the element, how it comes itself. Will typically always have values of 0. So this represents really our final state minus our initial state in this particular case when we look at a reaction. And if we do that, we will end up with 12 times minus 393.5 plus 6 times 286. We will then subtract it from basically 2 times 4904. And maybe put the numbers in right would be good. Try that again. There we go. And here we will end up with minus 6536, again, kilojoules. In this case, we will also see a negative here, which will tell us it is exothermic because of the negative that's present. Again, in terms of sig figs, we're really adding here, which means we should go to decimal places. That's a whole number, which means we really should end up with a whole number on that guy. This is 2 decimal places. This really doesn't matter at that point. So really our smallest in the overall subtracting that we're doing at the end is a whole number. So we'll take it to our whole number in this particular case. Any questions on how to calculate the delta H for reaction? So in chemistry, like I mentioned, that's probably the most common way that we can kind of determine, is it exothermic or endothermic? And a lot of times they will just give you the chemical equation like us up on top, and they'll just give you the delta H value. And from that sign that you see there, you'll know whether it's exothermic or endothermic. Any questions on any of that there? All right. So another sort of way that we look at energy is something that you're going to do today in lab, and also a very common sort of very easy procedure. And I think we looked at some of these just energy sort of diagrams before, and that is specific heat or specific heat capacity. And when we talk about specific heat capacity, the definition of it is basically the amount of energy that's required to change 1 gram of a substance by 1 degree Celsius. And there actually is an equation for specific heat, and that equation is Q is equal to ms delta T. These aren't negative or anything like that. It's just from PowerPoint, either none of those things there. Q here is heat or energy. And usually the units that we see for Q is either joules or calories, lowercase c for the calories. M is mass. And usually the units that we see for mass are grams in this equation. S is the specific heat capacity, and that has units of joules per gram per degree Celsius or calories per gram per degree Celsius. And S is the specific heat capacity. And that is the definition of specific heat capacity. How much energy, which is joules up on top, to change 1 gram, which is on the bottom, 1 degree Celsius, which is on the bottom. So that's really the definition. People oftentimes will confuse when they use this formula, Q and the specific heat capacity. So Q, which is heat or energy, should have just 1 unit, either joules or calories. And the specific heat capacity should have 3 units associated with it. So that's a very common thing that people mess up on. Personally, I use S for specific heat capacity. A lot of people use that. Some people, though, do use C for specific heat capacity, and some books use SH for specific heat capacity as the sort of symbol in the formula. So you may see it sort of written a couple of different ways, depending. I don't recall what your book uses, but I personally use S because it's just what's in my head. But S is common, C is sometimes common as well for specific heat capacity, and SH is sometimes used as sort of the symbol for it as well. Delta T is the change in temperature, and that should be always when you're using this equation or anytime, you should always do final minus initial. And one of the few things in chemistry that does not need to be in Kelvin, which temperature, is we leave this in degrees Celsius. And we leave that in degrees Celsius because typically speaking, our specific heat capacities are in degrees Celsius. So everything cancels out correctly. You take physics, they like to use Kelvin for this calculation, but here in chemistry, we leave it actually in Celsius. And that's kind of one of the few things that is left in Celsius when we're doing some type of calculation. Now, the difference between calories and, bless you, and joules is that conversion that we saw previously. 1 little calorie is 4.184 joules. And that is a conversion that you do need to know. The good thing about that is you also need to know this, which is the specific heat of liquid water. And by the way, that is the specific heat of liquid water. Specific heat capacity does change with the state. So as we'll see in a table very shortly, you could have ice or steam, which is also water, but they're in different states and they actually have a different value for specific heat capacity. But most of the time we deal with water in the sort of liquid state. So that 4.184 number is a number that we use a lot. And it's 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius is the specific heat capacity of liquid water. And again, that is something that you need to know. Yeah, so make sure you know that. We definitely will use it in a lot of calculations, especially when you're doing any type of specific heat type calculation. Is very commonly used. It is also very commonly used because we could use this like you will be doing today to do reactions where we mix solutions together, and solutions are really aqueous, and that means that they are water-based. So because a lot of solutions are water-based, which means they are aqueous, by knowing the specific heat capacity of liquid water, and basically if you got a thermometer and you could follow the change in temperature of the water or even the solutions that are changing, you could figure out how much heat or energy is being absorbed or released when you pour 2 solutions together and it does like a reaction, for example. And you could do this in a very simple sort of apparatus like you will use today, which is some nice styrofoam coffee cups, yeah, with a lid. So you put some styrofoam coffee cups, they work really well. Have a hole in the lid where you can throw the thermometer through it, and that's because it's very well insulated, which means it's not going to lose any heat to the surroundings. So everything that's going on and everything that you're measuring in terms of the change in temperature is going to be a result of what's happening inside the coffee cups, because it's not going to be affected by any temperature difference from the outside of the coffee cup. So that's why we use sort of an insulated coffee cups, and it's a very simple tool. And a thermometer is a very simple tool, and you can really determine a lot of things by doing that type of experiment. Any questions on that? By the way, when you do that type of experiment, like you're going to do today, and if you do it under constant pressure, which is typically most of the things that you do. When you actually calculate Q in this formula, it will be basically the same thing as the change in enthalpy. So by just simply using your thermometer, you could actually calculate the change in enthalpy for a particular reaction with a styrofoam cup and a thermometer, basically. And knowing the specific heat capacity of water is able to allow you to do that. You also can figure out in like kilojoules per mole, like those values are given in the table. If you know how much reactants you're starting with, you can convert those into moles and do some calculations as well. Any questions on any of that? Now, when we look at all these values in this table, or this formula, which is the Q is equal to ms delta T, mass is always positive. The specific heat capacity, or S, is always positive. So Q can be positive or negative. And again, the positive and negative for Q tells us the same thing as everything else that's positive and negative. If Q is negative, we're looking at exothermic. And if Q is positive, it is endothermic. So Q can be either positive or negative, but S and M are always going to be positive. So the most important thing here is what we talked about last time. It is actually the change in temperature, which is going to allow you to either end up with a negative value for Q or a positive value for Q. And that is why you always want to do final minus initial, because again, if something is releasing energy, their final temperature will be lower than their initial temperature. Kind of like your metal you're going to heat up today. It's hot, very hot metal. You're going to throw it into the water, it's going to get cold. And that means when you take the smaller number minus the larger number, you'll end up with a negative value for the change in temperature, which will give you a negative value for Q, which means that's all an exothermic type process, energy being released. Opposite of that, as we talked about, if your temperature goes up, and that means for that substance, your final temperature is larger than your initial temperature, which when you take the difference gives you a positive number for the change in temperature, and that will give you a positive number for Q. So sometimes people are taught just take the difference of the temperature. It doesn't really matter, but it does matter in terms of the outcome that you get for Q and whether or not you're able to determine is it exothermic or endothermic. So always take the final minus the initial. And when you calculate Q, if it is negative, you should keep it because it's telling you it's exothermic. Just like if you get Q that's positive, it's telling you it's an endothermic process. Any questions on any of that stuff there? So here's a table. And again, as we mentioned, you definitely should know the liquid water specific heat capacity and really both versions. I will say most of the time, even in chemistry, we kind of use the joule version of it more than probably the calories, but the calories does pop in there occasionally. And this is a good example, this table that you can see. All three of these things are water, right? But the other two are ice and steam, which is the solid and gas version of it. And you can see the specific heat capacity is actually different. It's more like 2 versus 4, as we see in liquid water. So it's really important to make sure that if you were doing some type of problem where you're dealing with ice changing temperature, you would want to use a specific heat capacity for ice, which is 2 versus the 4.184, which is for liquid water. Yep. Yeah, so if it just says water, you could probably safely assume it's liquid. But again, if you know it's either solid or gas form, which they probably would mention in the problem, hey, it's ice versus, water, or if it says steam or something like that, you would know it's in the gas phase. But probably safe to use always the 4.184 if it's liquid water. In most cases, it probably will be. But, you could have problems where it's really, in those other states. So you want to use the different ones. Yeah.
Other ones
You will be given the other ones, but you do need to know, they want you to know liquid water as you go through. So liquid water will not be given to you, but if it was something like gold or silver or iron, I don't even know it. So I would give it to you, obviously, in that case, but definitely the liquid water one you do need to know. Yeah. Other questions on that? Now, speaking of specific heat capacity, what does that mean? And we might have touched upon it last time as well. If I have a really large specific heat capacity, does it take less or more energy to change the temperature of a substance? You have a large value for specific heat capacity, is it more or less energy to change it? So if you have a really large, or if you have a large value specific heat capacity, it actually would be a more energy needed to change the temperature, right? So for example, something like water, which has 4.184 joules per gram per degree Celsius. What that means is you need to throw in there 4.184 joules for every gram to move it 1 degree Celsius, basically. So if you had something, say, like gold down here, you actually only need to throw in there 0.13 joules for every gram per degree Celsius. So it takes a lot less energy to do that. So I think we were maybe talking about the ocean water, right? And it goes up by, it's a very small amount of temperature, but it has a fairly high specific heat capacity. So it takes a lot of energy just to move it that little bit. Also, same idea when we're talking about the bathtub, right? And the difference in temperature between the bathtub, say, and the coffee cup. Coffee cup doesn't have as much mass of water in there, which means it doesn't take as much energy to get the temperature to start moving as you would need to heat up that bathtub of water to see a much bigger change in the energy or temperature. No, again, you just need to memorize the liquid water. That's one that they want you to know as you kind of continue through, your different courses. And they do want you to know both versions of it, the joules and the calorie version. So make sure you do know both versions. Although, like I said, you'll probably use the joules probably more than the calories in most cases. All right, so let's try one here. Determine the amount of energy required to raise 10 grams of aluminum, specific heat capacity 0.89 from 25 to 58. And let's do both. Okay, let's take a look. So obviously we're dealing with specific heat. So Q is equal to MS delta T. We have our mass given to us of 10 grams. We have our specific heat capacity of 0.89 joules per gram per degree Celsius. We have our initial temperature of 25. And we have our final temperature here of 58. So we really have everything that we need on this side of the equation, so we can plug it in. So our Q will equal our mass of 10 grams, our specific heat capacity there. And once again, we want to do final, which is 58 in this case, minus initial. And our degrees Celsius will cancel, our grams will cancel. That will leave us joules left over, which is good because we're looking for energy, which is Q, heat or energy. And if we multiply that out there, we got a little 10 times 0.89 times 58 minus 25 in that case. And here we end up with something like 293.7 joules. We're going to do a little sig fig action on that. That's like, not S, that's 3. This guy is 2. And when we do the difference here, that we also get 2, right? Based on 33 or something like that. And that means really perhaps we should end like 290 joules in this particular case to the proper number of sig figs. Question on that calculation? Yeah. You don't unless it asks you to do so. In this case, this would be endothermic as it's positive, right? So this metal is basically accepting that energy or absorbing that energy. And we know that from the difference in temperature, right? If temperature is going up, the only way for the temperature to go up, it has to pick up the energy or absorb it. It also did want us to convert to calories. So again, 1 calorie, 4.184 joules. So we can use the rounded number since we have it there. We'll do a little 4.184 joules per calorie. Joules will cancel. Yeah. 69.69 there. Calories looks good. In that case, I think you might get 70 if you didn't use the rounded number. So, fairly close to each other. Any questions on that calculation there? Okay, let's try another one then. We have 294 joules of heat is transferred to 10 grams of silver at 25 degrees. What is the final temperature of the silver if the specific heat capacity of silver is 0.24? So we're looking for the final temperature here in degrees Celsius. So see what you come up with. Okay, so let's take a look. So obviously we're again going to use our specific heat equation here. We got Q is equal to ms delta T. In this case, we got Q. So remember, Q has just the 1 unit. So that is what Q is there, the 294. We have our mass, which is 10 grams. We have our initial temperature, which is 25 degrees Celsius. We're looking for that final temperature, and we have a specific heat capacity of 0.24 joules per gram per degree Celsius. So if we put this into our equation, our formula here, 294 joules equals our 10 grams, our 0.24 joules per gram per degree Celsius. Our final temperature, which is what we're looking for, minus our initial temperature in this case. We need to first divide over, right? Basically, both of those numbers, we're going to divide to the other side. When we do so, grams go away, by the way, joules will go away as well. That will leave us Celsius that will flip up to the top there. And if we do that, 294 divided by 10 and divided by 0.24 gets us 122.5 degrees Celsius equals our final temperature minus 25 degrees Celsius. We do want to think about sig figs here as we're going through that. So I did a bunch of dividing, which means I should look at sig figs. So that's like basically 3, 3, and 2. So technically speaking, my number on the left there should end at the second significant figure, which would be right about there. Again, because I'm not really done with my calculation personally, I'm not going to round at this point. I'm going to continue on with my calculation, but I do want to kind of keep track of, what's going on in terms of the significant figures. What would be left at this point is we're going to add basically the 25 to the other side. So we're going to do our 25 here, which will take our 25 over here. That's going to get rid of that, obviously, on this side. Now, the last thing here we would do would be a 147.5 degrees Celsius would equal our Fahrenheit. The last math operation we did was adding, right? Technically speaking, this number here should be about 120, which is a whole number, yes, along with the other 25, which is a whole number since we're adding, which means our answer here should probably end up as a whole number as well, yeah? So again, I didn't really round because I was going to use that number in the rest of the calculation, but again, I kept track of it. And that's probably a little better than if you did use to round a number of 120 at that point. You would end up at like 145, I think. Might be a little off of where it probably really is. So again, we don't want to really round to the very end, but we do want to kind of keep track of everything. And by doing so, this will probably put us a lot closer to what the answer probably should be. Any questions on that there? This also makes sense in the idea of my initial temperature was 25, right? This is 294 joules, which is endothermic, which means my temperature should go up, and it did, right? So again, if you did this and you went less than 25, you're going in the wrong direction based on the energy that we see there, right? Because it's endothermic. Any questions? Yeah. It's not, so technically speaking, what the numbers we should have at the very end is really a whole number, right? The 25. And then really the 122.5 should go to 2 significant figures, right? Which means really, if we went strict on it, it would be like 120 basically. And that's 2 significant figures, but no decimal places, right? So the very last math that we did is adding. And we're basically adding 2 things that have no decimal places. So then our answer at the end should go to no decimal places because it's sort of the last operation we did. Other questions on that? Okay. So another really common sort of process when we're doing specific heat is exactly like the experiment you're going to do today. You basically can take, as we talked about, some styrofoam cups or something like that, and you basically can have some water in there, for example. And you could get the mass of the water, let's just say that we'd use like 110 grams of water. And we'll say that the initial temperature of our water was like 23.0 degrees Celsius. And you could take a piece of metal. So we got some water. We could take a piece of metal. And you could get the mass of the metal and we could weigh it out, and we'll just say we got like 85.0 grams of the metal. And let's say that much like what you're going to do today, you're going to take that metal, you're going to heat the crap out of it, right? And you're going to get it really hot. And you're going to start with an initial temperature, let's just call it 90. I trust you guys. You'll get to like 99 maybe. I'll say, well, maybe not 100, but we'll go 99 degrees Celsius. We got a really hot piece of metal. So when I take this hot piece of metal and I throw it into my water, which is at a lower temperature, in terms of the metal, will it gain or lose energy? It will give off the energy, right? It's going to release the energy. As we talked about, heat travels from hot to cold, right? So because the piece of metal is hotter than the water you're dumping it into, we're going to get an energy transfer from the metal to the water. So for the metal, it is an exothermic process, right? Which is important to keep in mind, because when we calculate something like the energy, this should be a negative value, right? For the water, it's going to be an endothermic process. It's going to pick up all that energy, which means that for the water, it should be a positive value when we calculate Q for it. So when I throw that metal in there, maybe my temperature in my water, maybe we'll just say it goes up to, why not 29 degrees Celsius? By the way, the other thing we know for liquid water, specific heat capacity is 4.184 joules per gram per degree Celsius. You always have that number, right? So that's oftentimes not given to you in problems, but it is a number that you always have. So you want to think about it like that. What will happen to my metal as it's sitting in that water? Where will it end up in terms of its final temperature? It will end up the same temperature as the water, right? Because it's going to equilibrate with the water temperature because it's taking a swim, basically, right? So it's hanging out there. It will basically cool down to the same temperature that the water heated up to. So by knowing the final temperature of the water, which we could easily do by just throwing a thermometer in it, you will also know the final temperature of the metal here will end up at 29 degrees Celsius. So let's say we wanted to know, much like the experiment today, what the specific heat capacity of the metal is. If we think about our specific heat equation, we could use it twice, one for the metal, and we could do it for the water. And if we think about the water's equation, we pretty much have everything we need to figure out, in this case, how much energy the water is going to gain. So we could do that to start with. We'll take our mass, which is 110 grams. We'll see how I did on my made up numbers here. We'll take our specific heat capacity. We'll do a little, again, final temperature minus initial temperature. And that's going to give us here that's going to give us something like 2761.44 joules, as the grams will cancel, degrees Celsius will cancel, and be left with joules. First off, we did end up with a positive number, which is what we would expect in this case, because the water should be picking up all that energy, right? And we see that as its temperature starts to increase, and it is positive. Now, in terms of significant figures, we should end up where in terms of sig figs? This number's got 4. That number's got 4. When we subtract this number, that is 6.0, not just 6, right? 6.0, because we're subtracting, which is 2 significant figures, which means really we should lay up our number, if we're going to stop the problem at this point, at 2 significant figures. Once again, I'm not going to really round at this point because I know I'm going to take that number and use it for the rest of the calculation. But again, I'm going to try to keep track of, where I need to be at the end. Any questions on that so far? Now, we know that in this situation, much like your experiment with the styrofoam cups, the only place that the water could gain the heat from was from the metal. So if the water gained 2,700 or so joules of energy, how many joules of energy did the metal lose? The exact same amount, right? The only difference is it is exothermic for the metal So the only difference is it's not positive 27. It is actually going to be negative 2700. So there's an important relationship of like Q of the metal in this type of situation equals minus Q of the water. So in this case, our Q of the metal will be minus 2761.44 joules, which means negative 2761.44 joules. So now by really simply taking a thermometer, some paper cups or coffee cups, and following the temperature change in water, we're able to figure out how much energy the water actually absorbed. But really what's allowing us to know is how much energy came off of the metal as it released that amount of energy. Any questions on that? That's important because now when we look at our specific heat equation for the metal, we now have the Q of the metal. We know the mass of the metal. We have the final and initial temperature. That is going to allow us to actually solve for the specific heat capacity of our metal, which is ultimately what we're looking for in this problem, and also your lab as well. So we will take S is equal to Q of the metal divided by M delta T. So using our negative value, once again, I'm not rounding at this point. I will round at the end, but I do know I should be about there. I'm going to divide it by the mass of the metal, which I made up 85 grams. And the second most important thing that you do here is final minus initial. The final temperature of my metal is which number? It is, yeah, whatever we ended up there, 29, yeah? Yeah. So it's going to be 29 minus 99. That's important because that's going to give me what type of number? Give me a negative number that goes with the negative that we got here. That will turn our specific heat capacity into a positive number, which is what it should be. So if we do that, we got minus 2761.44 divided by 85 and divided by our 29 minus 99. That's going to give us a specific heat capacity here of 0.46. The units do not cancel, so they all stay. Joules per gram per degree Celsius. And that is the definition of specific heat capacity, all three of those units, right? The energy, which is joules per gram per degree Celsius. I laid up at 2 sig figs. Why? This number here should have 2 sig figs, right? Basically, based off of our first calculation. This number is 3. And when you do the difference here, I think you end up with 3 as well, right? So in the end here, now I'm going to clean it up to what it probably should be, which is 2 significant figures. And again, by not rounding, we're probably, fairly close to probably what it should be. Again, if you went in with the 2700 or whatever it might be, you'll get a slightly different answer. And again, I probably went around in this type of situation to the end. Any questions on that there? So this is a very common way, and it's pretty much what you're going to do in the experiment today. You're going to just heat up the metal. You're going to get the temperature of the boiling water, which will represent the temperature of the metal initially, and you're going to dump it over into your coffee cup where you have the initial temperature and then the final temperature after the metal goes for a swim. By the way, this relationship works regardless of which one is sort of hotter and which one's colder. What would happen if I took the same water and my water temperature was, say, 30 degrees, and I take a piece of metal that was minus 2 degrees Celsius and put it in there? When I put a cold piece of metal into the water, which one is going to release the energy? Which one's going to absorb the energy? The water is actually going to release the energy. It's hotter, right? So the energy from the water, which is hotter, is going to transfer to my metal, which is colder, and it's going to be actually exothermic for the water, endothermic for the metal in this case, as it picks it up, right? It's kind of like when you take an ice cube out right in the air, it picks up all the energy from the air and it starts melting, right? So endothermic for the ice cube, exothermic for the surrounding air going into the ice cube. Any questions on that? So that opposite relationship, somewhere along the way, you need like that negative to switch around the opposite relationship of who is giving away the energy and who is absorbing the energy. But the actual value of the energy is going to be the same. So it's the same number, just the sign should be different. And that's what this is. Assuming no heat loss anywhere, you could add these guys up and they should equal 0, which means if you took like this guy to the other side, that basically is where we get the negative sign that we kind of did before. You don't have to really worry about this if you just remember what we basically just talked about. The Q of the metal is equal to Q minus Q of the water. That's basically the same thing. It's just you got to distribute that negative. It doesn't really matter if you call it Q of the water is equal to minus Q of the metal. It works the same. Just one of them's got to have that negative to basically be the opposite relationship of the other. All right, so why don't you try one here then and see what you come up with. 110 gram sample of a metal at 55.5 raises the temperature of 150 milliliters of water. Yeah, so let's take a look. So again, this is very similar to what we just talked about. It's identical. We have a piece of metal, and the mass of our metal there is 110 grams. We have the initial temperature of our metal, which is 55.5 degrees Celsius. We're going to put it into some water, which has a volume of 150 milliliters. It has an initial temperature there of 23.0 degrees Celsius. After the metal goes for a swim, 25.5 degrees Celsius. We always know the specific heat of water, which is 4.184 joules per gram per degree Celsius. We also know from our final temperature of our water that our metal should end up at the same temperature after it goes for a swim and it's sitting in there. And in this case, we are looking for our specific heat capacity of our metal. So once again, if we look on sort of our water side here, we have basically all the information that we need to go into this equation, except that's in milliliters and not mass. So if I have a volume and I want the mass of it, and especially if it's water, one other value that you should know, right, is our density is 1 gram per milliliter, right, of liquid water. So we could use the density is mass divided by volume, which means the mass would be volume times density, which basically means we have 150 milliliters times our 1 gram per milliliter, going to give us 150 grams of water. So we now have it in the right units. I am going to keep the same sig figs as 150.0 because some people use 1.00, 1.0. So you can kind of think of it almost like an exact conversion. So I'm not going to worry about the density value there. So we're going to put this in for our water. We have our 150 grams. We have our specific heat capacity of our water. And we have our final temperature of our water, which is 25.5 minus our initial, which is 23.0 degrees Celsius. And if we do that there, looks like we'll end up with something like 1,569 joules, as the grams will cancel, the Celsius will cancel. Significant figure wise, if we were to wrap it up right here, we should end up with 2 in this case, based off of the temperature difference is 2 significant figures, I believe. That is 4 and that is 4, right? So really we should be ending there. But once again, I'm going to use this in the second part of the calculation. So I'm not going to round at this point. I'm going to kind of keep the whole number. And that also tells me that the Q of the metal should be minus Q of the water, which means negative 1569 joules, as our metal was again hotter than our initial temperature of our water. So when it went for a swim, it is the metal that should be releasing the energy and should be negative and exothermic, while our water should be positive, like we actually got in our calculation, a positive value for Q for the water as to how much heat is being absorbed. Any questions on that there? Now for our metal, just like we did previously, we could rearrange the specific heat equation for the metal and solve for S, which would be our Q of our metal divided by M delta T, taking our negative version here, divided by the mass of the metal. And once again, also important, final temperature, in this case, 25.5, which is where it ended up. Started at 55.5, going to give us a negative number there. That's going to turn our specific heat capacity into a positive number. So divided by 110 and divided by 25.5 minus 55.5. Going to give us 0.48 joules per gram per degree Celsius. As nothing cancels, the number stays with the joules part. Once again, we do know we should end up here for this guy, which is really 2 sig figs. That is 4 sig figs. And when we subtract that, we get like 30.0, which is 3 sig figs. So we'll end up with 2 significant figures here on the back end of the calculation. Any questions on that? That again is a very, very common sort of way that we use specific heat, is to really just follow the change in water, and we could very simply figure out how much energy is being given or released in any type of reaction, or even in this case, not really a chemical reaction, but an exchange of heat or energy for something that is hotter versus something that is colder. Any questions? So clearly you need to be able to do these type of calculations. That's pretty much the identical calculation for lab. So just do it that way. You'll be fine, probably. Yes, in those cases. All right, so kind of finish up this chapter here and talking about energy. And I think we touched upon it the other day, but there is also another energy sort of value that kind of goes with nutrition, and it's sort of nutritional calories, which is the capital C here. And remember, 1 capital C calories is a kilocalorie, which is the same as 1,000 of the lowercase calories there. A calorimeter is much like what you're going to use in class. Can also be used to figure out the calories, for example, in food. They're sometimes called a bomb calorimeter because, frankly, you set the thing on fire. So you put your food, we'll call it a cookie right about there. You got a nice tank of water. You got a thermometer to measure the temperature change in the water. And that's a super well insulated sort of container. It's got some wires and oxygen. When you put a spark with oxygen, it sets your cookie on fire, right? And that's going to transfer all the heat basically to the water. And doing a very simple calculation like our specific heat equation, because we know the specific heat of liquid water is 4.184 joules. We could figure out, based on the change in temperature, how much heat was absorbed by the water. That would be how many calories or nutritional calories were released by the piece of food that you burnt, basically. So that used to be a common experiment. They would have people bring like Coke cans, put some water in it, put like a Cheeto underneath it and set it on fire and just let the Cheeto kind of burn. And as it does, it's heating up the water inside the Coke can. And you can find a difference in the temperature of that water, and you could do some calculations to figure out how many calories, lowercase, and translate that into nutritional calories by doing a conversion. Now, how we get, for example, those nutritional values that you see on labels on the back of food, there are caloric values for 3 really main types of food, and that is carbohydrates, fats, and proteins. They each have really a caloric value, and you basically take the grams of each of those times each caloric value, and that would give you, the calories that you see on nutrition label. Carbohydrates is 4 kilocalories per gram, fat is 9 kilocalories per gram, and protein is 4 kilocalories per gram. Remember, a kilocalorie is really a nutritional calorie, so it tells you basically how many calories there are. Anybody have like a candy bar, granola bar on them that's got a label on the back? Anything? No food? It's lunchtime, nobody eats food. They're just waiting for this class to be over. All right, then we'll look at the example I got in here, but we'll take a look at that example in just a second. But we'll take a look at it now since we just talked about it. So for example, if you had some cereal and it had 22 grams of carbohydrates and it had 7 grams of fat and 10 grams of protein, you could times each of those by their caloric value, and that'll give you the contribution of each of those to the overall calories. And if you add them together, for example, here in this cereal with some milk, it's 191 kilocalories, which is 191 nutritional calories. How they get that total where they say calories is 100 and something. They usually round down, oddly, for some reason. They round down on those calories when you do the calculation. But that's how they get those values. But more importantly here, let's take a look at really what the thing that you're going to do today, which is this is again constant pressure calorimetry, which can be done in those coffee cups like you're going to be doing today. And it can be all types of reactions. It doesn't necessarily, like I said, has to be like throwing a hot piece of metal into just water. You can't take 2 solutions, 2 reagents, mix them together, let it do its reaction. And as I mentioned before, because a lot of those are aqueous based or water based, we could just assume that they will have a specific heat capacity very similar to water because they're mainly made up of water. And by just simply a thermometer and some coffee cups, you can determine how much heat is gained or released in a reaction, even when you mix 2 things together, 2 reactants, and then the reaction actually takes place. And like I said, under constant pressure conditions, if you calculate Q, that is the same as really the change in enthalpy at constant pressure conditions. Now, the last thing to talk about here in this chapter is a little bit about sort of our equations and the energy associated with our equations. So as I mentioned before, sometimes this is very commonly the way that energy is sort of given to you. And in this case, we see that as we go from liquid to solid here in terms of water, that is the process of melting. It's an endothermic process. We see 6.01 kilojoules per mole. That's the energy required to do that phase change. Now, if we were going in the opposite direction, going from liquid back to solid, that's an exothermic process. Energy has to be released. And we see really the same amount of energy, regardless of which way you're going. But again, here, the sign is different. This is an endothermic process. This is an exothermic process. And what happens is if you have a reaction and you have to reverse the process, go from reactants to products, but really you're going to look at products to reactants. You have to reverse the reaction. What happens to the delta H value is the number stays the same, but the sign changes. So if it was a positive value going this way and you need to go back the other way, the sign goes from positive to negative, the number stays the same. And vice versa as you go that way. Sometimes we may need 2, say, waters versus 1 water. How that affects the delta H value is we would multiply the delta H value for that reaction by 2. So if you had to multiply by a common number across an equation, when you get to the delta H value for that, you would also multiply the delta H value. Also dividing, if you divided the bottom equation by 2, you would end up with the top equation. And that would mean that you would divide the bottom delta H by 2, and you would end up with the same Y as well. So if you reverse a reaction, you have a delta H for it, the number stays the same, the sign changes. If you have to multiply an equation by a particular number, you would also multiply the delta H value by the same number. And if you had to divide by a common number across an equation, you would divide by that common number. Now, this number here, where we transition from solid to liquid or liquid to solid, that happens at the normal melting point or freezing point of a substance. And say for water, that is 0 degrees Celsius where that occurs. By the way, that is what is sometimes referred to as the heat of fusion. And it's sometimes referred to as delta H of fusion. And just a reference point, that 6.01 kilojoules per mole is roughly 335 joules per gram. That is the amount of energy required to do nothing more than take ice at 0 degrees Celsius and change it to liquid water at 0 degrees Celsius. Not changing the temperature, but changing the state. There's a certain amount of energy required just to do that process, and that's known as the heat of fusion. The same thing happens when you go from, say, water in the liquid state to water in the gas state, or backwards. That happens at 100 degrees Celsius, which is the normal boiling point for something like water. And that is what is known as the delta H of vaporization, or the heat of vaporization. And for water, just for reference point, it's about 2,260 joules per gram. That also means at 100 degrees Celsius, you would be taking liquid water at 100 degrees Celsius and changing it to gas or steam at 100 degrees Celsius, not changing the temperature at all. Which one takes more energy to do? Going from solid to liquid or liquid to gas? It is the one where you go liquid to gas, right? Because at that point, you have to break everybody all apart from each other so they could go into the gas phase and start flying around. As you go from solid to liquid, it's only 330, which is much less, because as it goes from solid to liquid, it's just a little bit of movement away from each other, but they're still relatively close to each other, so it doesn't take as much energy. So how these relates actually to specific heat is whenever you're trying to calculate the heat or energy associated with a substance where it stays in the same phase, but the temperature changes, you use the specific heat equation, that Q equals ms delta T that we've been using. So for example, we took liquid water from 25 degrees to 30 degrees. That's all liquid water through that process. It just changes temperature, stays the same phase. You use Q equals ms delta T. If you're taking something where you're changing the phase, taking it from solid to liquid, but not the temperature, that is like a delta H of fusion. And you would use that for your calculation, not the specific heat equation. Or if you're taking something from liquid to gas and not changing temperature, you would use your delta H of vaporization. So for example, you could calculate how much energy would be required to take ice at like -2 degrees all the way up to gas or steam at 100 degrees. And there's actually, just to finish up really quickly here, there's actually just several stages that happens. So if we were to look at it, this is steam, which is like 100 degrees. This is liquid water, and this is ice, which is 0 degrees. If we were starting at -2, we would have to use specific heat equation to go basically to 0 degrees ice. We would then have to do a phase change at 0 degrees ice, which would be our delta H of fusion. We would then use our specific heat equation with the Q to go from 0 degrees liquid water to 100 degrees liquid water. We would do one more phase change, which would be our delta H of vaporization to end up with. So it's actually like a 4-step process in terms of energy. And you could do each of those steps separately and do the calculation. And the total amount of energy to do that would be just adding it all those steps together to get you to the final end. Any questions on that there? We will revisit, I think, delta H of vaporization